Welcome back. I'm glad you could join me for another go at trying to understand some of the math behind quantum mechanics. Last week I did sort of an introduction to linear algebra in the way that we saw how you can write out quantum states, and today we're going to expand on that a little bit by linking it to finding the probability of a quantum state. Now, I just want to say thanks to everyone who left comments on my last video like this. I found them really constructive. Some of you pointed out like mistakes in my pronunciation, but also ways that I could have explained things better, and I guess ideas that you had that I didn't include as well. Shout out to comment of the day from someone called Fred, who I guess left a lot of really constructive things in a comment, and one of the things he said was, when you were talking about spin, it was in a way that made it sound like it had solely to do with magnetic moment. In fact, spin is a carrier of angular momentum, one of the universally conserved physical quantities of nature. It is, however, a mysterious form of angular momentum, not being caused by any actual physical rotation. This is why it is often termed intrinsic spin, and seems to be one of those essentially quantum mechanical effects that can't be understood in classical terms. So thanks for that comment, Fred, because I think I didn't give like the best explanation of quantum spin, and I think maybe that builds a little bit more on what I said last time. Here's a little problem to get you warmed up. It's what we're going to work towards understanding throughout the course of this episode, so don't worry if you don't already understand the math behind it now. But it's the math of the famous thought experiment regarding Schrodinger's cat. In this thought experiment, we have a cat stuck in a closed box with a poison vial and a Stern-Gerlach analyzer, which can measure the state of a quantum particle. It can measure the particle to be either spin up or spin down, and this equation here represents the input state of that quantum particle. The particle is in a superposition of being spin up or spin down, and if the analyzer measures the particle to be spin up, then the poison will be released and the cat will die. So the cat is also in a superposition of being alive and dead. The question is, what is the probability of Schrodinger's cat being alive when we open the box, given that this is the state describing the quantum particle? Here's 3 options for you to choose from just to test your own knowledge, and there should be a little option up in the top right corner to have a vote. Last week I spoke about the dot product, or finding the inner product between 2 vectors, as a way to find how much overlap is between them. Now, I didn't, say in exact terms how to actually find this inner product, but I want to do an example of that using this color space example that I used to sort of set things up in the last episode. Now, say we have these 3 colors. Here we have pink, purple, and orange. They're made up of different amounts of red, green, and blue, and in this case it's like a decimal number where the maximum value would have been 1. Now, to find the inner product between pink and purple, we kind of expect it to be a reasonably high number, and saying that I mean it's reasonably close to 1. These vectors have been normalized, and so that means the length of the vector is 1. So if the overlap between them is 1, then they're pretty much perfectly overlapping. Alright, so to find the inner product, what we're going to do is take the first element of the pink and the purple, that's how much red they have in them, and times those values together. So it's going to be 0.7 for the pink times 0.5 for the purple. Alright, then we're going to add that value from the multiplication to the second element of both vectors multiplied together. So that's how much green they have. They both have 0 green. 0 times 0 is 0. Adding on 0 didn't change much. Now let's add on the product of the third element. So that's how much blue they have in them. It's 0.7 for the pink and 0.8 for the purple. Adding those 3 products together for the 3 elements that make up each color gives us a total value of 0.975. Now that's really close to 1, as we would expect, because these pink and purple are very similar colors. We would expect a lot of overlap here. So an exercise that I went through last time was this one here. We found the inner product, or the overlap, between the spin state up and this unknown state vector psi, which is defined as some amount of spin up, some A amount, and plus some amount, B, of spin down. And doing that gave us the answer A. I didn't ask you guys to do this, but it would have been very similar to repeat doing the same thing with the overlap between spin down and that same state psi. If you went through that one, you would find that the answer is B. And I asked you guys to do the inner product between the two psi states, and you would find that the answer for that was A squared plus B squared. Now, what are we going to do with all that? Let's try and do something with what we found here. So what we're going to say is that this unknown state, and remember we're calling it a ket when it's in these kind of brackets, we want this state ket to be normalized. That means you would expect, as before, that if you had the overlap between something and itself, the answer would be 1. 1 would represent complete overlap. So we already sort of, I guess, proved before that the inner product of this state and itself is A squared plus B squared, but we're also going to set that equal to 1, saying that it is normalized. So we've kind of given ourselves an identity to work with, because we also have a definition, I guess, for A and for B. That's what we also worked out before. And if we put in our A and our B into that equation too, this is the, I guess, final identity that we end up with. It's mostly just symbols here, but it becomes quite useful. If you look at it, each squared inner product term, so that's the thing inside the brackets, corresponds to a possible observed state. That was like up or down in terms of spin. And the sum of them, if you add them together, it has to equal 1. And we're asked by Brilliant here, what mathematical quantity has properties like this? This is how probabilities behave. If something has a probability of 1, that's like 100% of something occurring. If you have 2 possible options or events that could happen, and they're equally likely, they would each have a probability of 0.5 or half, meaning that if you added those two together, you'd end up with 1. Means something is certainly going to happen, but there is a 50% chance of it going one way or the other. That's very similar to what we're dealing with here in the quantum states. So this gets pretty cool, actually. If you look at this equation here, this is what we've worked up to. And what it means is that each of these squared inner product terms gives the probability of observing each of those states. So I believe the probability of observing a spin up state is given by this value here, and this is the probability of observing the spin down state. Now, because, you know, like this is equal to A, as we proved before, and this is equal to B, that means that A and B are probability amplitudes. The A and the B give us the probability of being, you know, spin up or spin down, and that's all wrapped up in this equation here. So we want to use this new thought and put it to the test to see if it can help us explain some experimental results. So we're going to finish this quiz and move on to the next one. So we're looking again at the Stern-Gerlach experiment. You guys corrected me that that's Gerlach, rhymes with back, which is probably not what I said last time. And that was this experiment that could measure, I guess, determine if a quantum state is spin up or spin down. It's using some neutrons coming in here that are in an unknown state. And the first analyzer here is, you know, separating them into spin up and spin down, I believe, and then they're passing into a second analyzer. So essentially we're being asked to use those expressions we've derived for the probability of each observation to figure out the likelihood or the probability of each of these question mark states. So if the unknown states already had been measured spin up in the first instance, what's the probability it's going to be measured spin up again or spin down? Now, you might be able to work this out just by thinking about it, but let's do it with the expressions we worked out. So we worked out the way we would figure this out would be the probability of being measured spin up in this second instance would be the inner product or the overlap of spin up and spin up. If they're normalized, we'd expect complete overlap there, and so the probability would be 1 squared, which is 1. So pretty much it's 100% that if something's already been measured to be spin up, then if you measure it again, it will also be spin up. That is sort of one of the inherent things about quantum mechanics, is that when you measure it, it sort of collapses into this state where continued measurements would give you the same result. So if we wanted to work out the second one, it would be the overlap between being spin up in the first instance and spin down in the second instance. Because there is no overlap between those two vectors, we've seen that before, they're at 90 degrees to each other, and they're two elements of our basis. So almost by definition, they have no overlap. And so the probability there is 0 squared, 0. This is impossible. In this next experiment we're going to look at, it's another Stern-Gerlach experiment. The first analyzer is as before. It separates the states into being spin up or spin down. And then it goes into a second one, which is aligned along a different axis. So it's rotated 90 degrees from the first analyzer. Its magnetic field is aligned along the x-axis, whereas before it was aligned along the z-axis. So when these neutrons are fired through, they're being deflected along a different axis. The magnet is in a different place. So what we see is that when we feed in something that's already been measured to be in the spin-up state, it's split equally into this spin left and spin right. 50 is the probability of each of these, so it's equally likely to be in either of these two streams. So what we're doing is we're thinking about how we can represent this mathematically. I guess how we write the probability of this happening. Now, the way that we write out these spin left and spin right states is as some linear combination of spin up and spin down. The A and the B are how much up and how much down to create the spin right, and then C and D similarly are the coefficients, how much spin up and spin down is involved in that spin left state. We know that the spin right and spin left can be written as a linear combination of some amount spin up and some amount spin down, because what we worked through last time was wanting to have, I guess, a well-behaved vector space. So we wanted to set up a basis that could span, that could create any possibility. So the basis that we chose was that spin up and that spin down state. We chose them because we could make any possible state as a combination of using them. So we can make one that points to the left and one that points to the right using these basis vectors, because that's what the basis vectors do. They can, I guess, make any direction. So this is how we do write it mathematically, that the probability of being either here or here, well, it's 50% each. So we write the overlap between this state and this state is a half, and similarly the overlap between this state and this state is also a half. It's actually a system of 4 equations, because we also have the similar experiment of being measured spin down and then being measured either spin left or spin right. We're being asked to determine the magnitude of A, which is, I guess, how much spin up there is, the probability amplitude of up in this spin right state. Alright, so have a little think about it. We do have 3 options here on the Brilliant quiz, that A is a half, square root of a half, or 1. Just have a little think about it yourself. I do happen to remember the answer to this one from my coursework days, that the magnitude of A is the square root of a half. Okay, so apparently 81% of people got that one right. Okay, so let's have a look at the solution. This is what we were starting with, the definition of what it means to be, I guess, spin right. And we knew this from that graphical experiment above, that this inner product is equal to a half. Now if we just kind of combine those two things, oh, the LaTeX keeps coming up, which is kind of annoying. If we write out the definition of spin right inside of that probability amplitude definition, we can take the A and the B out of the equations and we end up with a few more inner products, where remember, if they're both pointing up, full overlap goes to 1, if they're pointing in opposite direction goes to 0. So you end up with that all cancelling down to A. Which means that a half is equal to A squared, because don't forget those whole set of brackets were being squared. So yeah, if A squared is equal to a half, then A itself must be equal to the square root of a half. We can replace the A, the unknown, with 1 over the square root of 2. Now 1 over the square root of 2 is exactly the same as saying the square root of a half. You're just moving the square root down onto the bottom, because there's no point in taking the square root of the top, because that's 1 and the square root of 1 is just 1. So don't let that slight change in notation trick you. So really we've written out this spin left and spin right with sort of one less unknown. For the spin left state, had two similar unknowns, C and D, which are like A and B. But I guess if you sort of think through it, the C and the A are kind of the same, so that is also the square root of a half. So that's been replaced as well. Okay, so this course then goes in a little bit more detail, a bit more rigor through finding the value of the other two unknowns, B and D. I don't think I'm going to go through that whole derivation, but the result seems kind of obvious to me. They find that the magnitude of B and D is also the square root of a half. B and D do turn out to be going in different directions, so they have a different sign, and I think that sort of just comes out of some of this mathematics. Pretty much you find out that the spin left and spin rights are made up of equal amount of spin up and spin down, which again, it kind of seems obvious. And I think a similar thing works out if we skip through, like spin up and spin down could be also represented in the same way as being equal amounts or equal probabilities of spin left and spin right, and that's written in these two equations. There is one apparently important caveat listed here, and they say you might be tempted to consider the spin-up state as describing a set containing 50% of the neutrons in the spin left state and 50% in the spin right state, but this is not the case. The state describes a set of identical neutrons, each of which is in a state that combines the left and right states. So they're not saying that 50% of the neutrons that go through are in one state or the other. They're saying, I guess, that every neutron is in both of the states. They're in a superposition of both of the states. And that's a bit of a quantum mechanics word, which means, I guess, yeah, you are a combination of more than one thing at the same time. So let's put this all together a little bit and do one of the questions. They say, consider a beam of neutrons which has been prepared in an unnormalized input state, which can be described as, this here, 3 spin up plus 4 spin down. So normalize the state vector and predict the probability of observing it in either the spin up or spin down states. Alright, so let's work through this on paper, I think. So for a normalized state, if this is our A and this is our B, then we would have that A squared plus B squared is equal to 1. This is not what we currently have, because we have 3 squared plus 4 squared is equal to 25. So what we want to do is divide each of A and B by a normalization constant, such as when we do this, we want this to equal 1. So if we have 3 over 5 squared plus 4 over 5 squared, that would be equal to 1. So our normalization constant in this case is 1 over 5. So we could then write out our normalized state like this. Our probability of being in the spin up state is equal to the inner product between spin up and our normalized state squared. So that's going to work out to be a squared, which is equal to 9 over 25. That's the probability of being measured in the spin up state. Very similar for our spin down probability. It would be the inner product between spin down and our normalized state squared. Works out to be just the value of b squared, which is this, which is 16 over 25. And there's our probability of being spin down. So here's the solution to what you saw at the very start of the video. It's an example of the Schrodinger's cat thought experiment. In this version, a cat is stuck in a closed box with a poison vial and a Stern-Gerlach analyzer with an input state of chi, the Greek letter, the one that looks like an X here. So this chi input state is described by a superposition of spin up and spin down. The amplitude in front of both the spin up and spin down ket is this square root of a half. Now that's just been taken outside of the brackets, but it is the amplitude in front of both of those ket states. So the release valve on the poison vial is linked to the Stern-Gerlach analyzer, and the valve will be opened if a spin up neutron is measured. Before you open the box, the neutron is in a superposition of spin up and spin down, and the cat is in a superposition of alive and dead. We're asked, based on this input state, chi, what is the probability that Schrodinger's cat is alive when we open the box? So based on what we know, the probability of one of these states, I guess, occurring is you're going to take the amplitude in front of it and you're going to square that value. So if we're going to square the one in front of what we've got here, we're going to end up with a probability of a half. So that's the correct solution. Here we are, like this is exactly how you would do it mathematically. Here they're calculating the inner product between spin down and chi, which is, I guess, the probability that the poison vial is never opened. So you can just do 1 minus whatever you're getting out of this answer to find out the probability that the poison is opened. So they do that inner product and they write out chi explicitly as what we've been given to be its definition. You can take everything out, you end up with a couple of inner products that are very familiar to us now. This one is 0 and this one is 1. Try and follow through with that math right there. You'll get a half. It makes sense, I guess, intuitively, and now it makes sense mathematically. By the end of filming this video, I feel like I've been in my room talking to myself about quantum mechanics for so long that I worry it makes sense to no one except me. I guess that's my biggest fear putting this up, is that it just makes no sense at all, but it made sense to me in my brain. But yeah, try and let me know like if you could follow along with it and what I could do to change. If you want to follow along with the exact course that I'm using and try out some of the interactive quiz questions for yourself, then it's all on brilliant.org. Brilliant are a supporter of my channel, and you can go to brilliant.org/Tibees to sign up for free. You can also get 20% off an annual premium subscription if you're one of the first 200 people to follow that link. Thanks to Brilliant for supporting my channel, and I do hope you find their content to be useful. It's definitely helping me to relearn some of these concepts. Again, thanks for watching, and I'll see you in the next episode. I think there are maybe 1 or 2 more episodes of this math for quantum mechanics before we've fully covered this mathematical underpinning, and maybe we can move on to another topic after that. Totally open to suggestions of what that next topic would be.